Okay, Friedel crafts acylation, the next mechanism we need to learn, and it's another example of an electrophilic substitution reaction. So it should be very similar to the nitration of benzene that we did yesterday. So hopefully you'll start to recognize some of the similarities. Now, first thing, what is this acyl thing it's talking about? Well, that's another functional group that you haven't learnt yet, but you will. And it looks like this. So it's very similar to a carboxylic acid, but rather than an OH, it's got a Cl, which means it doesn't act so much like an acid. Remember, the R just means a chain of carbons. It can be as long or as short as you want, or as complicated as you want. But the important thing is, with these acyl chlorides, is that they are really, really useful in organic synthesis, because they can do loads of different reactions and react with different things in different ways to form different molecules, especially when you come to things like your acid anhydrides, carboxylic acids, amines, amides, and that stuff. And the other important thing is, it's got this carbon attached to it. And because it's got a carbon attached to it, if I substitute onto my benzene ring, I'm going to substitute this carbon onto it. So now I'm building a bigger molecule with more carbons in it. So if we think about what we did yesterday, we had to make the electrophile. An electrophile is your lone pair acceptor. And we've got this really electronegative chlorine, which already has lots of electron density close to it. A double bond to the oxygen, which is also really electronegative. So it's hard to see here where the electrophile is with that positive charge. And it's not here, that's why we can't see it. We have to react this with something. And we're going to react it with aluminium trichloride, AlCl3. That's really important. If you put that in the exam, you're likely to get a mark just for knowing that's the chemical you react it with. And what happens is it takes this chlorine off of the acyl chloride and puts it onto the AlCl3. And it takes this bond, or the electrons in this carbon-chlorine bond, with it. So what we're left with, I'll do this in a different colour so we can actually sort of see clearly what we're doing, is this group here. The carbon's got a positive charge because the electrons in that bond went away with it. And this species here with the positive charge is called the acylium ion. And this is going to be our electrophile. Now, the chlorine over here, that joined the AlCl3, and it took the pair of electrons with it. Because it's taken a pair of electrons, we're going to give that a negative charge. So this side's got no charge, this side also has no charge because the minus and the plus cancel out. So that's how we make the electrophile in Friedel-Crafts acylation. So now we can actually do the reaction. Let's have a nice benzene. Don't forget to put your circle in the middle. If you do forget to put your circle in the middle, you will lose a mark because you've drawn cyclohexane, not benzene. Now, we need to actually connect that ring up to make it slightly more accurate. Now, when we draw the nucleophile attacking this, we want to put it at the easiest possible angle for us. So we want the positive carbon to be closest to the ring, basically. So I'm going to draw it like that. Again, if you draw it in a different orientation, it doesn't matter too much, but this way just makes it clearer what you're doing. Now, yesterday, when we did the nitration, we had to draw a curly arrow from the ring to the NO2+. Well, we've got a ring here, we've got something with a plus charge, it's exactly the same. So we're going to go from the ring to the plus on the acylinium ion. This is going to make our intermediate, And we're going to play around with this carbon up here. So remember, that carbon's already got an H on it, which we're now going to draw because it gets involved. And we've got this Acylation group coming off the edge. And because we broke the ring, we now have to draw the partial ring here. Remember, you can't go past this point and you can't go past this point. Any smaller is fine. And don't forget, it's also got a positive charge now because we've taken electrons away from it. And then the final step is the bond to the hydrogen. The electrons from that go into the ring to reform the delocalized ring. So now we draw a full circle again. And now attached to our benzene ring is this. Now, what type of functional group is this? Well, you've got a carbon, double bond to an oxygen, so it's going to be an aldehyde or a ketone. And we've got a carbon here, we've got carbons in the R chain, so we've formed a ketone. Now, the other thing I hear you screaming out is, where's this hydrogen gone? Well, let's think about it. We've lost the electron, so it's become an H+. And what actually happens is a reaction between these two things, the AlCl4- that's still left in our test tube, because remember, this is all happening in one big test tube. Well, test tube size test tube, not big. So what we end up producing is HCl, because that Cl that we added onto that now comes and joins our hydrogen, and the AlCl3. So if we decide to write this all out as a big chemical reaction, we're going to have C6H6 for the benzene, plus R, whatever our acyl chloride is there, plus the AlCl3, and it's going to produce this benzene ketone molecule, HCl, and it's going to reform the AlCl3. So we've got this AlCl3 at the beginning and at the end. It's been reformed, therefore it's acted as a catalyst. So I kind of want to just give you a couple more examples of this rather than using a generic acyl chloride, using actual real examples. So let's say we start off with ethanol chloride. Which is that. So we've got two carbons, so it's an ethyl one. Or that's also how you might see it written, CH3 cockle, the acyl chloride group, often called a cockle group. So react that with the aluminium trichloride. Your acylium ion is going to be CH3 CO plus, because we've lost the chlorine, and we've also now got the AlCl4 minus. So just to show what this would actually look like in a reaction, rather than putting an R here, we're going to put the CH3 because it's a CH3 here, so we just put a CH3 here. Don't forget the plus. Curly arrow touching the ring, going to the plus. Then we're going to break open. So we're going to add it onto here. So again, where we had R in the last one, you're just replacing it with CH3. Have your partially open ring with a plus in it. As long as the plus isn't too close to that carbon, you're absolutely fine. Curly arrow from this hydrogen goes down to reform the ring. And we've got 2 carbons in our longest chain of our ketone with a big phenyl group attached. So this is phenyl ethanone, one of those weird ethanones which you get with this. And don't forget that you also produce HCl. Now, what happens if they give you a really horrible or more complicated acyl chloride than this? So what about something like this one here, which would be chloroethanoyl chloride, probably. So now we've got 2 chlorines involved. What's going to happen? Well, don't let it scare you. Ignore that chlorine on the end. This is the reaction that involves acyl chloride, so it involves this functional group. We don't care about that Cl over there at all. So we're still going to react it with our AlCl3. We're going to make, I'll put the plus on the carbon because it's more accurate, isn't it? So that's going to be our acylation. And then we've got the AlCl4 minus. And the only thing that changes with our mechanism here is that we add on a slightly more complicated bit where our R is. It doesn't get involved in the reaction at all. You just have to write it out so it's correct for the question they ask. I don't know why every example I've given you is attacking exactly the same carbon. But that's how I'm doing it anyway. So let's just have one last example. And this time, rather than starting with benzene, we're going to start off with methylbenzene. And you sort of don't need to know this for the A-level spec, but it's kind of interesting anyway, that if you've got a group like a CH3, you encourage substitution here, here, or here. If you've got a group like NO2 there, which kind of sucks electrons away from the benzene ring, then you substitute here or here. But we've got CH3 group up here, it's going to encourage substitution onto any of these points. If you then have your acylation, that's quite a big molecule that's going to try and attack it. If it tries to attack too close to the methyl group, there's not enough space. The methyl group gets in the way if it tries to attack on the number 2 carbon. So what normally happens is it attacks the number 3 carbon. So the CH3 doesn't actually get involved at all. That's wrong, isn't it? That's better. Hideously drawn, but hey hey. And what actually happens is that you substitute opposite the methyl group. If you ever go further in chemistry, it's important where you substitute on the benzene ring. But by adding different groups onto the benzene ring, so whether I add a methyl group or whether I add a nitro group, I can then control where I'm going to substitute my next thing onto because of the way it acts.